That's Rafa's approach to feedback.
Yeah, feel free to. Yeah. Hello. I'm the only representative from the aerodynamics group this week, and I'll be focusing on how we decided on the airfoil we're going to use, and what I've been doing in design of pilot devices. So, because our mission profile is actually quite complicated, it has different segments, there are quite a few things we had to consider. First of all, CL max, we wanted to be reasonably high, but that's pretty much for a lot of aircraft. So that would help us to reduce the basic area of the wing and the say weight. In our configuration, we wanted the CM, the pitching moment, to be as little nose down as possible because of the high mounted engines, which would produce nose down moment, and we want to balance it out for using the wing, at least not to make it too much, not to have too much nose down tendency. Lift over drag, we want to be quite high at the design CL, which is estimated at 0.264, the latest wing design, at least close to that. And last week we looked at the different thicknesses. We looked at 15% specifically, but it turned out that we have plenty of space for fuel, so we looked at lower thickness airfoils. And because our aspect ratio is quite low, structurally shouldn't be a problem. And also we would expect some drag reduction due to low thickness. And we tested different airfoils, NACA, RAE, GAWs as well, and we found that NACA 64 to 12 actually offers the best balance between these considerations. And a huge advantage of using a NACA airfoil is that we have experimental data on which we can build our design and analysis rather than numerical techniques, which can be unreliable, especially in close to stall conditions. Another thing we looked at when we chose the airfoil was maybe trying to utilize the drag pocket, which you can see on the right side, laminate drag pocket. But this data is for a Reynolds number of 9 million. And we try to predict what would be the transition behavior on our airfoil using X-foil. And it turned out that it separates almost immediately at 30 million, Mach 0.45. Therefore, it would be quite difficult to utilize the reduction in drag due to laminar boundary later. And we can see that these transition points basically correspond to the point where adverse pressure gradient begins. So right after the adverse gradient point, adverse gradient point, we can expect transition. Based on that, we extrapolated the Reynolds, the lift to drag curve for Reynolds number of 30 million, and in comparison, which doesn't have a laminar bucket anymore, so it's kind of flattened out. And based on this, we expect drag increase of around 12 to 13% based on the low Reynolds number estimate. So that's the airfoil. So the second thing I focused over this week was trying to design flaps due for the takeoff and landing configuration. I started with plotting the sectional CL max, lift coefficient, span-wise. It's not completely flat because Reynolds number changes. I used basically experimental data, 1.55, and I used empirical models to try to estimate it based on the Mach number we will be flying at around 0.15 during takeoff, cruise, takeoff and landing, quite similar. and there's a slight variation due to Reinis number. So then I used vortex lattice method to find the sectional lift coefficient at different angles of attack. And by increasing the angle of attack, I can estimate approximately the angle at which I would expect the 3D wing to stall. It is where the sectional CL touches the maximum lift coefficient. That's the point, the first section that stalls, so I assume the whole wing is stalled. So from this state at the angle at which the wing stalls is 21.35 degrees, which seems surprisingly high. But remembering that we have a low aspect ratio wing and that the induced angle is quite large, I tried to estimate the induced angle. This, by the way, is my hand sketch of the 2D and 3D lift curve, just for comparison. And using lifting line theory and assuming elliptic distribution, our wing was actually designed trying to keep the elliptic distribution. But Tommy will talk about it next week. The induced angle is actually 6.27 degrees, and the effective stall angle is under 15 degrees, so it's not that bad. So once I know the maximum CL, which was 1.38, I know how much lift I had to generate with the flaps, and I know these numbers, which are the maximum lift coefficient during takeoff landing, comes from our initial design, where we assumed the lift coefficient, which gave us our wing area. So increment for takeoff is 0.49 and for landing is 0.65. And the design of flaps is largely empirical because the main point is to basically reduce this gap between the maximum lift coefficient to zero. So and numerical techniques are, as I said, not very good at close to stall. So I used empirical methods described by Roscoe. So there are many things that we can play around with. It's the type of flaps, size of flaps, the deflection angle of flaps. Our baseline configuration dictates the type of flaps for the trailing edge at least, which will be plain flaps, which are simply hinged flaps that can move up and down. And for leading edge, I chose slats which are extending flaps for two reasons. One is because plain flaps are not the most efficient type of flap, and we need more increment of CL max. Therefore, we utilize slats which are the most efficient of the leading edge flap configuration. And the other point is that leading edge slats give a big increase in the nose-up pitching moment, which can be very beneficial, especially in takeoff from water, where we expect huge nose-up moment from engines and the drag of the water. As for layout, I plan to utilize the whole wing for leading edge slats. Stability team gave me the dimensions of the ailerons, so I used the rest of the span for the plain flaps of 25% chord plain trailing edge flaps and 6% chord leading edge slats. So Roscoe method is basically empirical, and it involves multiplying a lot of coefficients together, which are read from graphs. I'm not including all of them here, but one of them is the deflection angle, and that's the only thing I'm changing in this design. So I extrapolated the curve and obtained this graph where we can read of the CL lift coefficient increment from the deflection angle of the trailing edge flaps. And we can see that with leading edge flaps deployed, we need 15.3 degree deflection of the trailing edge flaps, and during landing 38 degrees. So that's what I've done so far this week. What I'm going to do next is basically analyze the flap configuration and estimate the lift curve with deployed flaps, and I'll try to also calculate the contribution of flaps and landing gear to drag. And next week I plan to start on aerodynamic analysis during the tactical cruise, how we call it now, which will be close to surface flight. So I'll have to estimate the optimum flight velocity and height for this stage, and yeah, which basically the main part will be quantifying the effect of the ground effect. That's it. Thanks. Questions?
Seeing you were so afraid that everyone was me.
How does it feel when you called for questions and nobody says anything?
Yeah.
Well, either it means that everyone understood everything, or no one understood nothing.
Exactly.
And so you've got these flat angles at the end.
Yeah.
You didn't comment on whether you thought it was reasonable or not.
Yes, I actually varied the geometry of the flaps. I could have played around with the flat chord, which would give me this curve basically shifted up or down. And I made it so that the deflection angle during landing is around 38 degrees, which is a usual value, I'd say. And shouldn't increase drag too much, because if we go higher than 45 degrees, the drag increase will be quite substantial.
You don't really care about drag during landing. You actually want it. But yeah.
Yeah.
For takeoff, you are right. However, 15 is good. If you go back to your revised CL versus CD curve.
Yeah.
So this curve now shows us that before you had an optimum L over D at 0.2 something, right?
It will be a bit lower.
Now it's going to be lower, or where is the optimum now?
This picture doesn't include the x-axis, but it will be around here. So it will go from this point to over the blue dashed line, which is the estimated for 29 million Reynolds number.
Is that light blue slope?
That's
gradient of 1?
It's the gradient.
No, it's
the tangent.
Gradient where the actual, if you wanted to fly at the maximum L over D, that would be your design CL over here. This is a lift and that's drag.
Because yesterday I
So yeah,
this airfoil picture we've been trying to make out. It doesn't perform as what the usual Raymer, the Bible says. So if you actually have a laminar bucket, the L over D should give you a very high gradient when you actually touch the bucket point. But this airfoil doesn't. When you actually touch the bucket, it actually have a slow L over D ratio, then you actually reach outwards to get higher L over D. So maybe there's something we can improve on the airfoil geometry, see whether we actually need to change the shape or anything, depending on. Because we can never be sure about experimental data on 28 million or 29 million. That's based on the mean aerodynamic chord, mean geometric chord, Reinis window. That's what they normally base it on. And we can never scale the curve to the extent of accuracy that we can do in wind tunnels, like what the NACA does. But we only scale according to the ends of, for example, the 6 to 9 million, but we scale for every square of the ends, it go down to about 3 million. But we know that there will be a transition to turbulent flow, and the CF will be increased, even though the stall is delayed. So the estimation of drag is quite important for the fly sim when they try to make the wing, and plus it's quite important for us when we try to choose the airfoil. But with the limited data we have for 29 million, we can only do a very limited amount of things with what we have.
But basically what I'm saying now is that if this revised drag polar is to be believed, then this airfoil is not fit for purpose. Because you get your maximum L over D at 1.5.
Well, our
At a CL of
design,
1.5.
our design lift coefficient is very low, and it's very hard to find the airfoil that has that lift coefficient. Because this is actually one of the best ones. Others are actually more shifted towards the right side. This was actually one of the best ones, and that's not the only thing we looked at when choosing airfoil. We also gave a very good compromise between CL Max and CM, because the general trend is that high lift airfoils have very high negative pitching moment, and this airfoil can provide high CL Max with relatively low nose down pitching moment, which was very important for us. So here we see that it's around minus 0.1. That's the minus 0.25. That's the pitching moment. For high lift airfoils, it's usually around minus 0.1. So somewhere here. Another thing about this is that transition basically is dependent on the value n critical, which is set to 9 here, and it's basically a parameter which describes the disturbance of incoming air. But it's quite difficult to quantify it for our purposes, and online research didn't really tell me what the optimum value would be for our aircraft. So I use 9, which seems to be the most common value everyone uses.
Pretty convincing CP got there. Next one. Yeah. Not going to maintain laminar flow through that suction peak.
Yeah. And no separation as well during cruise.
Which is surprising, since there is actually quite clearly a laminar drag pocket for the experimental road.
It's true, you get a lot on the lower surface. So.
Yeah, the low surface, it's around here, where adverse pressure gradient is, so half before.
Did you try to see if you could use X-foil to validate the experimental, or to validate X-foil with the experimental? Did it give you a similar drag pocket?
It did give a drag pocket.
Okay.
However, the difference was a bit bigger than I would have expected, also in terms of lift slope.
Yeah.
Although if I look back, I tested a Mach number of 4.45, and I don't think the wind tunnel tests were around top of 45. So the maximum CL was very low for X, well, usually overestimated.